Okay, so we're going to focus on using free body diagrams to quantify forces that are acting. And so we're going to start with this situation right here. So imagine we have this object that weighs 5 newtons. It's being suspended in air. There's something pulling it up at an angle here and something pulling it off to the side. And so if we know what its weight is, so how hard gravity is pulling it down, and if we know how hard it's being pulled to the side, then we can actually solve for this other force here that's pulling up on it at an angle. We can solve for both how strong the force is and at what angle it's pulling. Okay, and so the key here is that we know that this system is in equilibrium, so it's got a constant speed because it's at rest, which means that all the forces have to be balanced. Okay, and so we can actually kind of solve for how hard it needs to be pulling this way and that way. So we have this force at an angle. Okay, how hard does this force need to pull to the side to balance out this object? Well, it needs to balance out that 10 newton pull, so it's got to pull back this way with 10 newtons. And how hard does it have to pull up? Which you need to pull up with 5 newtons of force. Okay, so 5 newtons. And then from here, we can solve for this. Okay, we can use triangles. We could say, okay, the magnitude of this is going to be equal to the square root of 10 squared plus 5 squared. Okay, and then the direction is going to be equal to the inverse tangent of opposite over adjacent, or 5 over 10, or 1/2. Okay, so we solve for those things. We find that the strength of the force is about 11.2 newtons, or the magnitude, and then this angle would be about 26.6 degrees above positive x. Okay, and so we found the magnitude and direction of that force. Okay, and that's one way to go about it, but what we're going to use is something else called net force equations that are going to become really important for us. And so to solve for things like this, what we do, we'll label this as force T, and we're solving for the magnitude of T and its direction. And so the way we do this is by setting up equations. And so since this system is in equilibrium, we know that the sum of the forces horizontally and the sum of the forces vertically have to be equal to 0, since it's balanced up and down and balanced side to side. And so the way that we use this, we actually use summation notation. We're going to say the sum of the horizontal forces, since it's balanced, we're going to say that the sum of those horizontal forces will be equal to 0. Okay, and so if we say that we have a traditional coordinate plane with that being positive x and this being positive y, we'll say that, okay, for x, if I could draw like a dotted line right here, I have 10 newton force acting in the horizontal plane, and then I have this force right here, this tension pulling up at an angle, is partially acting in that plane. Okay, but it's just that horizontal component. So I can say, okay, we have the horizontal component of the tension acting in the positive direction, and then acting backwards in the negative direction we have 10 newtons. Okay, so from here we can say, okay, well, Tx minus 10, and then we'll say, okay, so Tx equals 10. Okay, and we can say, okay, well, if that's the x component, that's the angle, then this would be T cos theta equals 10. Okay, and so we use the horizontal forces to figure this out, and now we're going to write a separate equation for the sum of the vertical forces. So we're going to sum up all the vertical forces. Forces are also balanced up and down, so we're going to say that's equal to 0. And then we say, okay, we have the upward component Ty, or we could say T sine theta, since it's that part that's pulling up. Okay, and then downward we have the 5, so we say minus 5 newtons. Okay, and so we get that T sine theta is equal to 5 newtons. Okay, and so from here, what we can do is we can put these equations together, and for this one I would actually recommend to solve them, you could divide them, but you could solve them both for T and set them equal to each other. You could solve it for theta and set them equal to each other. I'm not going to do that because that's going to be too much work. But we could say that, like, we could put this one on top, so T sine theta equals 5 newtons, and we're going to divide that by t cos theta equals 10 newtons. And so the t's will cancel out, and we'll sine over cosine, which is tangent. So this would be 5 over 10 is 1/2. So tan of theta equal to 1/2. Then you could use inverse tangent, and you'll find this angle. And then from there, you can plug the angle in to either this equation or that equation to then solve for t. Okay, and this is a kind of a complicated way of doing this. It's simpler just to figure this part out the way that we were discussing. And then I think it'd be a little bit easier to take that approach. Okay, so going over here though, we have another scenario where in order to figure this one out, we're going to need to use net force equations. Okay, and so we have this force A and force B that are, so we have some kind of system that's suspended like this, and we have an object that's hanging down, pulling down from it, and we want to, these angles are not the same, it's attached, and so we want to find out how much it's pulling this way and how much it's pulling that way. If this object wasn't attached and is allowed to, like there's a pulley here, then they might be pulling even, but since they're not, we can't do that. So what we can do though is we can set up again net force equations. So we're going to start with by finding the net force in the x direction. Since it's in equilibrium, we can say that's equal to 0. We'll again say this way is positive and that way is positive. So we'll say A cosine of 25 minus B cosine 40 equal to 0. Okay, and if you want to, you can say then, okay, I'll add that over and then divide by cosine of 25 so that A is equal to B cos 40 over cos of 25. Okay, and then you could punch that into your calculator form. And then the sum of the forces for y, we'll say, okay, it's balanced, so it's going to have to equal to 0. Okay, the net force, we call this the net force, is equal to 0. And so we have upward AY, or A sine 25, and we have upward BY, the y component of B, so plus B sine 25. And then we have this downward 40 newtons, so minus 40. I would say, okay, we'll bring the 40 over. Or really, from here, what you would want to do is basically plug this in for B, and you could solve it. Okay, we won't go through that step right now, just because I don't think it's necessary at this point. But this is a situation where you need to use these net force equations for x and for y. Okay, and generally we're not going to be in a situation this complex. It'll be much simpler than that. Okay, which will bring us to our next example. So here we have a block connected to a string going over a pulley connected to another block. And you can imagine this situation that the whole system's going to go this way. It's going to accelerate that way. But it turns out it's at rest. And the reason it's at rest is because something is holding this guy in place. So the first thing we're going to do is we're going to draw a free body diagram for each object. We're going to do this one right here and this one right here. So let's start with this one. This object has a weight equal to 20 newtons. Okay, and then what's pulling up on it and how hard is it pulling up? We have tension pulling up with a force of 20 newtons. Okay, and we just have these two vertical forces here, but we could do some of the forces for x. If we wanted to solve for tension, we could say 0 equals the upward tension minus 20 newtons downward, and we solve that, we get the T equal to 20 newtons. Okay, now for this scenario right here, we know that we have weight downward, in this case equal to 30 newtons. We have a pull this way from tension. Okay, how hard do you think tension is pulling it that way? Well, we know from this previous part that tension is pulling with 20 newtons, so we're going to put 20 newtons there. Okay, and then these forces are balanced because the situation is, it's in equilibrium, and in this case it's at rest. So we know that this is balanced and that's balanced, so we're going to draw in forces here and here. And this would be a normal force, and this would be static friction. Okay, so for our normal force, we need to find how strong it is. So we can say sum of the forces for y. And in some cases, you don't need the equation. Like this one, you can figure out without the equation. So we'll say upward normal force minus the downward weight of 30 newtons. Okay, we'll add this over, and we get the normal force equal to 30 newtons. So we'll say, okay, that's equal to 30 newtons. This was tension. Okay. And then we want to solve for the static friction there. Okay, same thing, sum of the forces for x. We'll say, okay, 0 equals the tension of 20 newtons minus our static friction, and say, okay, static friction then would be equal to 20 newtons. Okay. Alright, and then for this last scenario here, we have a block hanging from a pulley, and that's attached, the cable that's running through the pulley is attached to the ceiling, and then it runs to another pulley, and then there's someone pulling on it down here. So we want to know how strong the pull is. Well, if we do a free body diagram for this pulley, we'll call this T1, and this T2, and this T3. Okay? So we'll say, okay, so for this, we'll do a free body diagram for this pulley right here. So pulling up on it, we have T1 and T2, and then pulling down, we have the weight of the pulley, or the weight of the block equal to 30 newtons. So we want to solve for T1 and T2 here. And so we'll do a vertical net force equation, so the sum of the forces acting in the y direction, they will be equal to 0 because it's balanced. Okay, and so say T1 plus T2 minus 30 equals 0. Now this is not enough information to solve it. Okay, we can't figure it out from here because we don't know what T1 and T2 are. Okay, but it turns out there is another piece of information we have. What we do know is that with a pulley, if this pulley is like what we'll call an ideal pulley where it spins perfectly freely and it has no mass, we'll talk about the whole mass situation later, but let's pretend for now it has no mass, then T1 would be equal to T2. Okay, so we're going to say that for all situations where the pulley has no mass and can spin freely, that the tension on either side is equal because there's nothing stopping it from balancing out. Okay, and so we have the same amount of tension on both sides, so T1 equals T2. So we could just rewrite this as T1, which means that 2 times T1 minus 30 equals 0, or that T1 equals 15 newtons. Okay, and so to balance this out, we're pulling up with 15 this way and 15 this way. Well, given what we know, if we're pulling up 15 this way, the same amount of tension here would be the same as the tension right here on the other side, so it would be 15 over here too, which means that the pull would be equal to a total of 15 newtons of force. Okay, and so here someone is actually able to suspend something that has a weight of 30 newtons by only applying 15 newtons of force. Okay, and so this is why pulleys are useful. They allow you to hold something that's heavy by using less force. Okay, and some of the force, there's going to be force pulling on the ceiling right there, and there's force pulling on the ceiling right there. And since we're pulling down, if you look at this whole system, you're pulling down with 15, and the block is pulling down with 30, which means that the ceiling has to be pulling up with 45 total newtons. So some of that comes right here, and the rest comes right there. Okay, but pulleys are useful for reducing the amount of force required to lift something, and so people use these to lift really, really heavy objects for this reason.